In this video, we're going to look at a magnetometer. So this will help us to get directional measurements off of the true magnetic north. So let's go ahead and get started. So let's look real quick at this figure. Right, we have our true north, which we can denote coming out of the aircraft as I superscript V. So that's in our vehicle frame. Right? We have what's called magnetic north, and note that magnetic north doesn't align with true north, right? There is this difference. We call this, so if we're flat, if we're looking at the flat plane, the difference angle is delta, right, between our true north and our magnetic north. Now if we were to look from the side, we'll get our inclination. It's our vector is not going to be pointing in the northeast plane. It might point into the earth or up out of the earth. And so that's known as the inclination. So we have the declination by this delta, and we have our inclination. So we can define the magnetic north using from our inertial frame or from our vehicle frame, using both the declination and we already had declination written, and our inclination. Okay, so let's stick with this value right here. I think this description is slightly confusing. Instead of writing it like this, let's say that we have our magnetic north and we'll call this frame M. So this is our magnetic north in the magnetic frame. Okay, it's just going to be equal to our elementary vector, where we have 1 in the x component and 0 in the y and z, right? So if we allow this rotation matrix to be the rotation matrix from the magnetic frame to the inertial frame, and if we look at this, our transpose, so this, if we were to say that this is R from the magnetic frame to the inertial frame, our transpose would go from the inertial to the magnetic, but we've not written it like that. So the way this is written is not correct, right? So we have from the inertial to the magnetic. Okay, and then we can just cross this guy off and we can say this is M in our magnetic frame, right? So then we have all of the notation that we're familiar with. This guy, the transpose, would then go from our magnetic to the inertial, right? And we just have this transform from our magnetic to the inertial. We take M superscript M, which is our magnetic vector in the magnetic frame, which is just E sub 1, E sub 1. And we take it into the inertial frame. And we can transpose it one more time from the inertial frame to the body frame. So this transform right here, and we're just rotating from the inertial to the body frame, and we get the body frame measurement of the magnetometer. So again, all we're trying to do is get this vector M in the body frame. And the measurement then is given, we're just going to say, hey, the measurement is given by M superscript B. So this is the magnetic vector in the body frame. So in the body frame. And we're going to have some additive white noise. White noise. Okay, excellent. So that's the model we'll use for our magnetometer. Okay, so the next two slides just talk about declination and inclination. So declination, you can see based on where you are in the earth or on the earth, this declination vector from the true north y-axis to the magnetic north y-axis varies as you change your position in the earth. So in Provo, it's 12.5 degrees. That's where the authors are. And then our magnetic inclination is basically the dip into and out of the Earth, and that also will vary based on where you're at on the Earth. But either way you have it, given this rotation matrix, assuming that you're in a relatively localized location, that rotation matrix is going to be constant, and we can generate our magnetometer measurement using that equation.